Drop a glass from your hand and it shatters on the floor. Flip a switch and the light turns on. Press the brake pedal and the car slows down. From childhood, we absorb a simple structure. One thing happens, and because of it, another thing follows. Cause produces effect. The world feels stitched together by invisible threads of necessity. Pull one thread and something must move. It seems obvious. It feels undeniable. But pause for a moment and ask a more careful question. What do you actually observe? When the glass falls, you see it slip, descend, collide, break. You see a sequence. When the switch flips, you see a finger move, plastic click, light bloom. Again, a sequence. At no point do you see causation itself. You see events unfolding in order. One follows another. The mind supplies the glue. This distinction feels trivial. It isn't. It's structural. We are so accustomed to linking events that we rarely notice the leap. We assume that because B follows A must have produced B. But the production itself is never visible. It is inferred. We experience succession, not necessity. The feeling of inevitability is something we project onto patterns that have repeated reliably in our past. David Hume noticed this centuries ago. He argued that causation is not something we perceive directly. We perceive constant conjunction. Fire is followed by heat. Gravity is followed by falling. But the must that connects them exists in expectation, not sensation. The mind, trained by repetition, anticipates the future and calls that anticipation a law. You might resist this. After all, physics gives us equations. Newton's laws predict motion with extraordinary precision. Surely that is more than habit. Surely that proves that causes really produce effects. But even Newton's equations describe how variables change in relation to one another. They do not expose a hidden engine labeled causality. They map regularities. If you know the position and velocity of a planet, you can calculate where it will be later. The math is powerful. Yet what you have is a rule connecting states across time, not a visible thread pulling one into the other. The difference matters because we rarely question it. Cause and effect feels like the backbone of rationality itself. Remove it, and thought seems to collapse. How could science function without it? How could planning, responsibility, or explanation survive? That reaction reveals how deeply embedded the assumption is. We do not merely believe in causality. We rely on it to structure meaning. Every explanation we offer takes the form of, this happened because of that. Every argument assumes that reasons produce conclusions. Every moral judgment presumes actions generate consequences. It looks foundational. It feels unavoidable. But foundations deserve inspection. What if cause and effect is not a primitive feature of reality, but a framework we impose to navigate it? What if the world does not contain arrows labeled cause and effect, but only events arranged in patterns that we interpret? The question is not whether events are related. They clearly are. The question is whether the relation is what we think it is. To see how deep this runs, we have to move beyond everyday intuition and into the place where causality seems strongest, the clockwork universe of classical physics. For centuries, the strongest reinforcement of causality did not come from philosophy, it came from physics. When Isaac Newton wrote down his laws of motion, he did more than describe how objects move. He offered a universe that appeared mechanically inevitable. Give him the position and velocity of a body, and he could tell you where it would be tomorrow. Provide the forces acting on it, and its future unfolded like arithmetic. The implication was breathtaking. If every object obeyed precise mathematical laws, then the entire cosmos operated as a grand machine. Every event was the necessary result of prior conditions. The fall of an apple, the orbit of the moon, the tides of the ocean, each followed inevitably from what came before. The world was not merely ordered, it was determined. This was more than predictive success. It felt like metaphysical confirmation. Cause and effect were not just habits of thought, they were embedded in the equations governing reality. push an object and it accelerates. Increase the force and the acceleration increases proportionally. The structure seemed clean, linear, unambiguous. A cause produces a measurable effect. Imagine knowing the position and velocity of every particle in the universe at a single instant. In Newton's framework, that knowledge would, in principle, allow you to compute the entire future and reconstruct the entire past. Pierre-Simon Laplace famously imagined an intelligence vast enough to perform this calculation. For such a mind, nothing would be uncertain. The future would not be open, it would be fixed. Determinism became the dream of certainty. Not only could we explain events, we could, in theory, predict them with total precision. The universe resembled a clock wound at the beginning of time, ticking forward with flawless necessity. Causes did not merely precede effects, they guaranteed them. And yet, even within this apparent perfection, subtle cracks began to form. Classical equations are deterministic, but they are also sensitive. In many systems, especially those involving multiple interacting bodies, tiny differences in initial conditions can grow exponentially. This is the insight behind chaos theory. Two nearly identical starting states can diverge dramatically over time. The equations remain deterministic, yet prediction becomes practically impossible. This does not destroy causality, but it complicates it. The chain of cause and effect remains intact, yet our ability to trace it weakens. Determinism survives in principle while collapsing in practice. The clock still ticks, but its gears are so intricately interlocked that no human mind can follow them indefinitely. More importantly, even in its most elegant form, Newtonian physics describes relationships between quantities. It tells us that acceleration is proportional to force and inversely proportional to mass. It tells us how trajectories evolve, but it does not expose a metaphysical engine labelled necessity. It provides equations linking states across time. The universe appears inevitable because the mathematics is consistent. But consistency is not the same as ontological proof. We observe regularity, encode it in formulas, and interpret that regularity as causation. For 2 centuries, the clockwork model dominated thought. It was stable, comforting, rational. It reinforced the intuition that every effect has a precise cause waiting to be uncovered. Yet the more closely physicists examined nature, the more they discovered that this mechanical picture was not the final layer. At the smallest scales, the clean chain of inevitability begins to fray in ways Newton could never have anticipated. The first real fracture in the clockwork dream did not come from philosophical doubt. It came from experiment. When physicists began probing matter at atomic scales, they expected smaller gears inside the same machine. Instead, they found something far stranger. Consider the double-slit experiment. Fire single particles, electrons, photons, toward a barrier with 2 openings and detect where they land on a screen behind it. If the particles pass through one slit or the other like tiny bullets, you would expect 2 distinct clusters. Instead, you see an interference pattern, alternating bands of light and dark, as though each particle behaved like a wave passing through both slits at once. Even more unsettling, when you attempt to measure which slit the particle actually goes through, the interference pattern disappears. The behaviour changes. The act of observation alters the outcome. What seemed like a straightforward causal chain, particle passes through slit, screen registers impact, becomes dependent on whether information is extracted. This is not a failure of measurement. It is not a technical glitch. The probabilities predicted by quantum mechanics match experimental results with extraordinary precision. The theory does not say that we are ignorant of hidden causes. It says that, fundamentally, outcomes are described by probability amplitudes. Before measurement, the system does not possess a definite value in the classical sense. It exists in a superposition of possibilities. In classical physics, if you know the present exactly, you know the future exactly. In quantum physics, even with complete knowledge of the wave function, you can only predict probabilities. The theory provides precise statistical forecasts, but not determinate outcomes for individual events. The future is not fixed in detail, it is distributed. This distinction is crucial. The randomness is not merely epistemic, arising from lack of information. Bell's theorem and subsequent experiments have ruled out broad classes of hidden variable explanations that would restore classical determinism. Nature appears to resist being reduced to pre-existing, definite properties waiting to be revealed. Cause and effect begin to lose their classical clarity. When a radioactive atom decays, what causes that specific moment of decay? The theory supplies a half-life, a probability distribution over time, but it does not identify a preceding trigger that necessitates that exact event at that exact instant. The decay is not caused in the Newtonian sense. It is governed by probabilistic law. This does not mean that anything can happen without structure. Quantum mechanics is tightly constrained. The probabilities are not arbitrary. They follow precise mathematical rules. Yet the transition from possibility to actuality, the collapse of the wave function if one adopts that language, does not resemble a classical push producing a classical response. The discomfort here is profound. If fundamental processes are indeterminate, then causality, at least in its strict deterministic form, is not basic. What we call a cause may instead be a statistical condition that shapes likelihoods rather than guarantees outcomes. It is tempting to believe that a deeper theory will eventually restore certainty. Perhaps beneath quantum mechanics lies a hidden mechanism that re-establishes inevitability. Yet so far, every high-precision experiment reinforces the same message. At small scales, the universe does not unfold like a clock. It branches like a probability tree. If causation at the quantum level is not a rigid chain, but a structured distribution, then the classical picture is already incomplete. And this is only one axis of disruption. On the largest scales, another revolution was waiting, one that would challenge not only causality, but the order of time itself. If quantum mechanics unsettles causation from below, relativity unsettles it from the side. The disturbance does not come from randomness, but from time itself. In classical intuition, time is universal. Events occur in a single shared order. First A happens, then B happens. The sequence feels absolute. But Einstein showed that this ordering depends on perspective. Consider two events occurring at different locations, say two lightning strikes hitting opposite ends of a moving train. An observer standing on the platform may judge them simultaneous. An observer riding inside the train, moving relative to the platform, may judge one to occur before the other. Neither observer is mistaken. The difference arises from the finite speed of light and the geometry of space-time. This means that simultaneity is not universal. There is no single cosmic clock ticking in the background, imposing a master sequence on all events. Order becomes relative. For events separated in space, what counts as first can depend on the observer's frame of reference. At first, this seems like a subtle technicality, but causality relies on ordering. If cause precedes effect, then the structure of time must support that direction. Special relativity preserves causal consistency through one crucial constraint. No influence can travel faster than light. This creates light cones, regions of space-time that define which events can affect which others. Within a light cone, one event can influence another. Outside it, influence is forbidden. This preserves a kind of causal order, but it also reveals something deeper. The separation between past, present, and future is not as clear as everyday language suggests. In the block universe interpretation, space-time is treated as a four-dimensional structure. Past, present, and future are not flowing states, but coordinates within a geometric whole. From this perspective, events do not come into existence one after another. They simply are, located at different points in space-time. This reframing shifts the role of causation. Instead of imagining the past generating the future, we may instead describe relationships between events embedded in geometry. The arrow of cause pointing forward becomes less a dynamic production and more a structural relation. It is important not to drift into mysticism here. Relativity does not deny that events are connected. It imposes strict constraints on how they can be connected. But it challenges the intuition that the universe is unfolding moment by moment in a single universal sequence. If the future already exists as part of the space-time manifold, then saying the past causes the future may be a simplification imposed by our perspective as beings moving along world lines. Our consciousness experiences time as flowing. Physics describes space-time as structured. The tension deepens. Quantum mechanics suggests indeterminacy at the smallest scales. Relativity suggests that temporal order is frame-dependent. Together, they erode the idea of a simple, linear chain of causes pushing reality forward. What remains intact is correlation, constrained by geometry and probability. Events relate. Influences propagate within limits. But the familiar image of causes striking effects like dominoes begins to look less like a fundamental feature and more like a convenient model. If both the microstructure of matter and the macrostructure of space-time complicate causality, the question becomes unavoidable. Is cause and effect an illusion? Or is it something subtler, an emergent pattern arising from deeper laws that do not resemble it at all? After all this disruption, it is tempting to swing toward extremes. If quantum events are probabilistic and temporal order is relative, perhaps causation is simply false. Perhaps the chain we rely on is nothing more than a cognitive mirage. But that conclusion would move too quickly. The breakdown of fundamental determinism does not erase structure, it reframes it. At human scales, the world is remarkably stable. Glass falls and shatters with reliable regularity. Planets follow predictable paths. Engines convert fuel into motion. The probabilistic blur of quantum behavior averages into consistency when trillions of particles interact. Randomness at the smallest scale does not translate into chaos at the largest. It smooths out. This smoothing is crucial. In complex systems, fluctuations tend to cancel. What remains are statistical regularities so tight that they mimic necessity. The motion of a baseball does not reveal quantum uncertainty in any noticeable way. The equations of classical mechanics remain extraordinarily accurate in ordinary conditions. Cause and effect appear rigid because, at our scale, the probabilities are overwhelmingly skewed. In this sense, causality may be emergent. It is not the bedrock of reality, but a higher-level description that becomes valid when microscopic indeterminacy and relativistic geometry settle into stable patterns. Just as temperature emerges from molecular motion, causation may emerge from underlying relations that do not themselves resemble it. This does not make causality meaningless. It makes it approximate. When we say that striking a match causes a flame, we are describing a network of physical interactions that unfold with such consistency that deviation is negligible. The language of cause and effect compresses vast complexity into usable terms. It allows prediction, planning, and explanation within a domain where the approximation holds. The mistake would be to mistake the approximation for the foundation. Newton's equations work with stunning precision in many contexts, yet they are not the deepest description of motion. Similarly, everyday causation works with stunning reliability in ordinary life, yet it may not be the deepest structure of reality. This layered view resolves the tension without dismissing intuition. Cause and effect is not a lie, it is a map. At certain scales, the map aligns almost perfectly with the territory. At deeper levels, the territory is shaped by probability amplitudes and space-time geometry, rather than simple linear chains. The illusion persists because it is useful. Evolution favored minds that link events, anticipate outcomes, and infer patterns. A creature that failed to associate fire with heat would not last long. The brain builds causal narratives because they compress information and guide action. They are adaptive models. What shifts, then, is not our ability to reason, but our understanding of what that reasoning captures. The world is not a row of dominoes falling in strict succession. It is a structured network of relations constrained by law, filtered through probability, and embedded in space-time. At our level, those relations behave so consistently that they resemble necessity. So cause and effect is not wrong, it is incomplete. It works astonishingly well within its domain, yet it is not the final word. Beneath it lies a reality where outcomes are distributed, where temporal order depends on perspective, and where what we call causation may be a shadow cast by deeper symmetries. And that realization does not collapse meaning, it expands it.